So in today's class, we are going to talk about few very important theorems of group theory. Though the proofs are not till now within our syllabus, but at least the statements are there. And especially for finite group theory, these statements are very important. And for many competitive exams, you will find problems that deals with this kind of theorems. Okay, so the theorems that we are going to start today or talk about is the Cayley's theorem. The proof is very much within our syllabus. So Cayley's theorem, Then we will talk about Cauchy's theorem. Though the full volume of Cauchy's theorem is not within our syllabus, but we will state that theorem, but we'll do a particular case of that theorem. And then we will state Sylow's theorem. The problem set that I have given to all of you deals with all of these problems. So after getting the information about this theorem, at least the statement of this theorems, you will able to recognize that few problems can also be solved. So I will give my best so that you will able to understand the statement of the theorem. The proof requires little bit advanced technique that will be done in your when you will be in your 5th semester. So till now you'll have to wait, or I must say that those who are interested to see the proofs are requested to have a look at the proof. But in general, I'm not going to discuss in this class because within our syllabus, the proofs are out of scope. But suddenly it's not that advanced level things that will be required to prove this. For example, if you know a particular kind of thing known as group action, that's not very difficult. Then you will able to understand a proof of Sylow theorem. There are other ways to prove Sylow theorem, but if you know group action, then the proof is very easy. Similarly, for Cauchy's theorem, you require a little bit more results. And also for other things, you require the finitely generated abelian groups. The concepts of finitely generated abelian groups, So this kind of concepts will be required that are within the syllabus of your 5th semester or when you will be at your 3rd year level. Then you will understand, or you will have to read all those theorems because they are mandatory. Okay. But believe me, they are not that difficult. So if somebody is interested, some advanced students are there, he or she must have a look at all those proofs. But for the time being, we'll go for the proofs of Cayley's theorem, and then the statement of Cauchy's theorem and Sylow's theorem, both the statements. But we'll also try to give a proof of a particular case of Cauchy's theorem for finite abelian group. But in this class, what I am planning to explain is that not only this theoretical description, but I want to provide you a basic kind of historical development of this group theory. As I promised almost at the beginning of my course, that I will also explain about a historical development, and then you will able to understand that while dealing with this historical development, during that time we do have lots of misconceptions. Okay. For example, if I ask you this simple question, Lagrange's theorem, and if I ask you the question, who discovered Lagrange's theorem, a certain answer will be suddenly this Lagrange's discovered the Lagrange's theorem. Similarly, when we talk about abelian group, okay, so you know that the same thing as commutative group. And if I ask you the same question, who discovered this abelian group, your certain answer will be Abel must have discovered the concept of abelian groups. But through this lecture, I will try to show you that is not exactly the case. and due to the changes of historical data and all, few person actually discovered and the name has been given due to their honors. Okay, so that I will come to it later on. But first, let us have a look at the basic concepts that we started with. So we started with the concept of groups. And when we talk about groups, the definitions are pretty obvious. So the closure property, associative property, identity, and the existence of inverse. So in our first class, we have already mentioned that if we talk about like in that way, if the definition is like this, G is a non-empty set and star is a binary operation or composition on G, then from the definition of binary operation or composition, you do not require the first property, that is the closure property. Because by definition of a function, it's a binary operation. That means it must be a function from G cross G to G. As a result, since this is a function, if you take two elements, say G1 star G2, which can be written as star of G1 comma G2, because if I treat this as a function, then star of G1 G2 by definition it will always be within G. It cannot go out of the G from the definition of a function, which is nothing but a mapping from G cross G to G. As a result, you can see that always for all G1 G2 belongs to G, G1 star G2 will always be within G from the definition of the star itself. That means from the definition of binary composition. In that way, if you define like this, then you do not need to mention the closure property separately. It's already there within the definition of binary composition. In that case, we can say that this G star, where star is a binary operation on the non-empty set G, satisfies the following three properties: associativity, identity, and the existence of inverse. If these three properties are satisfied, then we call it as a group. So we all know about this fact. If I ask you the question, who gave the definition of these groups, then it will be a really challenging question. Actually, it's really not known who has all given the formal definition of group. Though we read this definition of group in that way, in an axiometric way, but it was not, the history says that it was not from the very beginning that the concept of group came with this kind of axiometric definition. It's Jordan and Dirac. So they are considered to be the forefather of this concept of axiometric definition of group theory. That means Dirac and Jordan, they actually came up with this axiometric definition that we read today. Okay, this axiometric definition were actually given by them. If we look little closer, then when we when we go into a little deeper study of group theory, then few theorems like Lagrange's theorem, abelian group, normal subgroup, and Cauchy and Cayley's theorem, they came into picture. So today we are talking about this Cayley's theorem and then Cauchy's theorem, and at the end we will also talk about the concept of the Sylow's theorem. Okay, but as I mentioned, if you look at little carefully, then the concept of the historical development of these concepts will be quite clear. Okay, so let us first try to have a look at what is Cauchy's theorem, Cayley's theorem. Okay, so let's have a look at the basic idea of what is Cayley's theorem. Okay, the statement is quite simple. What Cayley did is basically he was actually dealing with kind of groups, but believe me, at that time Cayley did not have any idea about the axiomatic definition of groups. At that time, most of the cases, the people, they deal with either permutation groups, so they deal with permutations or polynomials. So during that time, the group concept was not there, but most of the results that were actually developed later on, which actually came through the study of either polynomial or solving some system of equations, and then some permutation groups. Okay, what Cayley's theorem states that every group G is a subgroup of of the permutation group on G, of the permutation group so usually we call it as AG on G. So what do you mean by the permutation group AG on G? So you know that, so G is a non-empty set. So AG may be considered like this. AG is nothing but the set of all bijective mapping from G to G, such that F is a bijective mapping. So bijective mapping means from G to G, that means F is a permutation. So AG is the collection of all permutations from G onto G. Okay, and we know that with respect to this composition of functions, this forms a group. Okay, so what Cayley prove that take any group, maybe 5, then consider AG. AG is the collection of all permutations from G to G. Okay, so each element of AG is nothing but a permutation from G to G. What he says that every group is isomorphic to a subgroup of the permutation group AG. That means there must exist a copy of G which is isomorphic to G. That means there must exist a subgroup, say SG, of AG which is isomorphic to G. That means structural wise, algebra wise, or you can say that algebraically, these two groups are same. That means they are identical if we consider with respect to isomorphism viewpoint. Okay, so what they understood, or what initially Cayley thought, that okay, then it's sufficient to think about the permutation group, and then for every group there can be a kind of representation using the permutation or the elements of AG, because this is a subgroup of AG. So SG, each element must be a permutation. So consider any group, then you can think of every element of G. So there must be an isomorphism. That means for each element here, there is an one-to-one correspondence with some element, and that element must be a permutation. So every element of G can be represented in terms of a permutation group. Okay, so that was his idea. Okay, so let us try to prove. I'll just give you a kind of hints how to prove this. Okay, so what is given here for every group? That means a group is already given to you. So this is given. So I need to construct some SD, right? Okay, so for every element, say A belongs to G, let us define a mapping FA from G to G defined by f of A evaluated some element, say B of G, equal to A B. So if you consider this to be star, this group, then A star B. So you can understand that A star B, A was an element of G, B was also an element of G, then A star B will also an element of G. So this belongs to G. Okay. So let us define a mapping. So there is no doubt that this is a mapping. Then the question is, what extra properties does this mapping has? Can anybody tell me? What can you tell about this FA? Okay. So question, is FA injective? Is FA surjective? So what is your argument? True or false? Anybody? Okay, let's see whether FA is injective or not. Okay, so if A, say B1 equal to FA B2, if and only if, what is the definition? A star B1 equal to A star B2. Then if and only if, what it should be? You can multiply both sides by A inverse, then it becomes B1 equal to B2. And then what is your conclusion? So this is if and only if. That means if A B1 equal to F B1, or in other way, A not equal to B implies F A not equal to FB, or if B1 equal to F A B2 equal to B1 equal to B2. Then what do you say? That implies FA is what?
So well defined and
FA is well
one
defined and injective.
one.
Well defined and injective. Very good. So this is if and only if, mind that. Now what we need to show? So FA is injective, that is true. Now the second question is whether FA is surjective or not. What is your intuition? Is FA surjective? So what we need to do? So we need to take some elements. Let B belongs to G. So you are taking something from right. So FA is a mapping from G to G. So this is your FA. Take some element from B. What you need to show, you need to find some element here of which if you apply FA, you will get B. So can anybody tell me what should I write? Then FA of this equal to B. What should I write here? It's very easy.
E, E,
What?
identity.
Identity. Think about. What is the definition of FA?
So A inverse B.
Very good. So A inverse B. Why? Because if I consider this, then by definition, it should be A star A inverse B. And that is nothing but by associativity, you will have this bracket and that becomes E and that becomes B. Okay. So that means A inverse B, that is very much an element of G. So for this B, there exists A inverse B belongs to G such that if A of A inverse B equal to B, that means if FA is surjective. Clear? Then what is your claim? If you have both this, then finally what will be your conclusion? FA is a permutation. Thus, FA is a permutation. Okay, permutation. Clear? Now consider SG. Sorry, S. What I have given, S of G. Okay. Now consider S of G. All such FA from G to G for all A belongs to G. So take any A from G, consider FA, and consider all such functions. Okay. So if A, the collection of all such FA, that is we call it SG. Okay. Clear? Is the construction of SG clear? So we consider only one map FA. So if you vary A, then you will get different FA. If you vary A equal to B, A equal to C, A equal to D, so on, then you will able to vary all such A, and then your FA will be different. So take all such FA, okay, by varying A over G. So this will be a set. Claim. That is very important. Claim. SG is a subgroup of AG. What was AG? Remember, AG was the collection of all permutations from G to G. And SG was a special kind of permutation, FA type, where FA is defined like this. So this is must be bigger. It consists of all permutations from G to G. And we have shown that this is a permutation. So this is a particular kind of permutation. Now, if you vary all such A belongs to G, you will get different FA and take the collections of all such different FA. So that is SG. So SG is no doubt a subset of AG. No doubt about that. I claim little more. I claim that SG is a subgroup of AG. Somebody able to tell me how to prove that? How will you prove? What are
So
the
first,
things? Yeah, what are the things you need to prove?
closer. Oh, sorry, AB inverse.
Before
If
that,
of
you need to prove that
Sir,
this is a
basically
non-empty.
the identity mapping is always here because identity mapping is a biject is a permutation. So identity mapping is always in SG. So SG is non-empty.
Okay, so how will you explain identity mapping? You need to define like this. Okay, so he says that fx equal to x, you can write in this way. How? Fe of x is basically e of x, and that is x. So you know that identity mapping is, so this is the, for all x belongs to G, so this is a permutation, we all know. So this is always in AG, and we have, you can also write this as this, same thing. So this mapping is within SG. As a result, SG is non-empty. Next, what you need to show? That take any two elements. So from SG, you need to show that, what do you need to show? You need to show basically take any two elements, say let FA, FB belongs to SG, to show FA, FB inverse belongs to SG. Sorry, AG. Yeah, SG. If you are able to prove this, then you are basically done. And to prove this, you will require few of the things. What do you mean by, how do you define this one? That is important. If you are able to define this, then you will be done. So it's not very difficult. Can anybody tell me how to define this one? How to define FB inverse? So what is FB inverse? Any guess? So you need to define at some point, say C. How will you define? Okay, let's have a look at what is FB inverse of C. What is that? FB inverse of C is B inverse of C, right? Now, any guess how to define this? So FB was a permutation, so FB inverse will also be a permutation. That is not a problem. The problem is how will you define this? I'm giving you a hint that this part will play an important role. See, here inverse is on the B, and here the inverse is on the F, and somehow they are related. Okay, so I assume that you will do. So this is a homework. It's not very difficult. You can try. It's very easy. You can think, and then you will. I already gave you the hints, so it's now very easy. This is the only tricky part. Okay. So suppose you understood that SG is already a subgroup of AG. Now what you need to show? You need to show that original G and SG, they are isomorphic. So it was your original G and this is your SG. Now you need to define a mapping phi, say from G to SG. How will you define a mapping from here to any guess? Phi of some element of say A. How will you define? How will you define a mapping which should be from G to G? It's very easy. Yes, please, anybody? It's already there on the screen, so you can very easily write this part. How should I define? So that that element should belongs to not SG. What I need to yeah, SG. That should be belongs to SG. Any guess? It's already there. This symbol is already there on the screen. Okay, tell me any element which involves A and an element of SG. Any element, such element, which involves A and that is an element of SG. If you remember the definition of SG, what was actually SG?
Sir, if suffix A.
Very good. F suffix
Sir.
A. Very good. So just now we have seen that. What is our SG? SG is nothing but the collection of all such elements. All such elements. So the elements looks like this and it involves A and A comes from G. So you need to define a mapping phi from G to SG. So you take an element A from G and then you need to map it to some element of SG. And you know that if A is fixed, then you can always construct an element of SG which must look like this form. Okay, where f of A defined at B is defined by A star B. Okay, and that is defined for all A belongs to G. Then you can very easily prove that this phi is an isomorphism. Okay, that you need to prove, and that's all. Then if you're able to prove that, so I'm just also again leaving this as an homework. So if you are able to prove that, then what you have actually proved, you proved that G is isomorphic to a subgroup of AG, where AG was your permutation group. So now you can very easily understand that every group may be finite or infinite. So I haven't talked anything about whether the original group is finite or infinite. I just took any group and I just used the application or the operation defined on G and AG, that's all. So you can now understand that every group can be thought of as a subgroup of AG, the permutation group on G. Is the idea clear to all of you? I just gave two homeworks and that's not very difficult to prove. One is proving that this is a homomorphism. Another one is to prove that what is the relation between this. I mean, how to define this one. That's all. Okay, any question till now? Is it clear or shall I repeat once again? Is it clear to all of you or shall I repeat? Clear? Okay. So that's all about Cayley's theorem. Okay. Now let us have a look at another very celebrated theorem, which is known as Cauchy's theorem. And in many exams, in many competitive exams, you may find some of the results from which are being used in proving that results you require Cauchy's theorem. The statement is very easy. Okay, Before going to Cauchy's theorem, let's have a recapitulate few of the things, few are old things. Like we have already heard about Lagrange's theorem. Lagrange's theorem. What it states? Anybody? What is Lagrange's theorem? Anybody please state? Anybody? Anybody please? What is Lagrange's theorem?
For any finite order,
For any finite order, very good. For any
finite group G, the order of every subgroup of G divides the order of G.
very good. For any finite group G, the order of a subgroup of G must divide the order of G. Okay, that means if you take any subgroup of G for a finite group G, then the order of the subgroup must divide the order of the group. Very good. Now, if I ask you the question, we have already seen, is the converse true? Is the converse true? Many interview, these questions are very frequently asked. Is the converse true? What is your answer? The answer is no, big no. Give some example. In our class, we have already seen in A4, there exists no element of order, how much? In A4, what was the proof? Or in A4, no subgroup of order?
6.
Yes. So you can prove in that way in A4, 6 divides order of A4, which is 12, but there exists no subgroup H of order 6. Okay. So what is the converse of Lagrange's theorem? Lagrange's theorem's converse should be, suppose order of G equal to n, then for every positive divisors, there must exist some subgroup of G. So that's the converse of Lagrange's theorem. But in case of A4, we have seen that the order of A4 is 12 and 6 is a positive divisor of A4, but there exists no subgroup of A4 whose order is 6. So the converse of Lagrange's theorem is not true. Very good. So the next question could be, in which group the converse of Lagrange's theorem is true? So the question is, in which group the converse of Lagrange's theorem is true? Any idea? Anybody?
So cyclic groups.
It should be finite cyclic group. Your answer is correct, but most of
Finite
the students,
cyclic.
yes. So little bit you have to be little careful while giving the answer, because in the interview board, they actually, many students, they remove this part. They understand it properly, but when they give the answer, most of the cases they forget to talk about finite group. Okay. So answer is, for any finite cyclic group, the converse of Lagrange's theorem is true. Okay. I am going to give you another example, what we have already mentioned, but I didn't give a proof. Today also I'm not giving a proof of that. That is, for any finite abelian group. So it was cyclic group. Now I am also relaxing it, finite abelian group. The converse of Lagrange's theorem is true. So as I mentioned, when you are going to study about finitely generated abelian group, then you will study this result. Okay. So the question is, it may happen that the whole converse of a Lagrange's theorem is not true, but can it be partly true for some special cases? That's very important. And Cauchy gave that answer. So what is the statement of Cauchy's theorem? Cauchy's theorem. So what is the converse of Lagrange's theorem? Just remember. So if order of G, so let me I think it's better first write it down, the converse of Lagrange's theorem first, then it will be more clearer. Converse of Lagrange's theorem. It states that let order of G equal to n, that means finite group, and D be a positive divisor of n. Okay, then there exists a subgroup H of G such that order of H equal to D. That means for every positive divisor D of n, there exists a subgroup H. Okay, that's the converse of Lagrange's theorem. And as you know that in case of a cyclic group, for every positive divisor of n, there exists a unique subgroup. It may not be unique. For example, in case of K4, Klein's 4 group, you know that in case of a Klein's 4 group, the converse of Lagrange's theorem is true, because here you have E, you have EA, you have EB, you have EC, and then EABC. That means K4. K4. So its order is 1, this order is 2, its order is 2, its order is 2, its order is 4. So you see that in case of K4, the order of K4 is 4. And all the positive divisors of K4 are 1, 2, and 4. So they are the only 3 positive divisors of 4. And you see that for each of this positive divisor, for 1 you have one group, subgroup. For 2 you have actually 3 different subgroups, 3 subgroups. For 4 you have one subgroup, the original one. Okay. But in case of a cyclic group, for example, if you consider Z9 plus, then for this, the positive divisors are 1, 3, 3 square. And the subgroups which are there is this one. For 3, you will have 0, class 3, class 6, and Z9 itself. So you see that for each you have unique. So this is for 1 exactly 1, for 3 you have exactly 1, for 9 you have exactly 1. But that is not the case for K4, because K4 is not cyclic, but Z9 is a cyclic group. So that's very important. Okay. So converse of Lagrange's theorem both holds for K4 as well as Z9, but with respect to that, you have some difference. Here you might have more copies of the same group, but all of them are isomorphic. See, all of them are isomorphic. But here you will have exactly one copy of the subgroup, not a repetition. Okay, that's the specialty of cyclic group. For every positive divisor, there exists a unique subgroup in case of a cyclic group. Okay. So you see that in case of converse of Lagrange's theorem, if it has to be true, then for every positive divisor, D could be any positive divisor, there must exist some subgroup. Okay. But it may not be true in case of a 4. We have already seen that 6 is a positive divisor of 12, but there exists no subgroup of order 6. So the question is, it may not be true for every positive divisor. Can you give some positive divisor for which the converse of Lagrange's theorem exists? That means for that positive divisor, you will always have a subgroup of that order. Okay, so that's the Cauchy's theorem, and it states like this. Okay, what it says? So Cauchy's theorem. It says that let G be a group, so G be a finite group. Okay, let's write it once again. Let G be a let G be a finite group of order n and P be a prime number such that P divides n. That means P divides the order of the group. Then there exists a unique, sorry, there exists not unique, there exists a subgroup of G of order P. See here, what is the difference between this? Is for every positive integer there exists a subgroup, which happen for cyclic groups, finite cyclic groups. But in Cauchy's theorem, it says that here P is a positive divisor of n. That's true, but it has a special extra property that it has to be prime number. If that is true, then you do not need to have G to be a cyclic group. See, now Cauchy's theorem states about for any finite group. That's the very important observation. So the converse of Lagrange's theorem is true for cyclic group, that we all know, finite cyclic group. But here the statement is true for any finite group. Okay, but the point is here D was any positive divisor, but now my D is a prime divisor. And if that is a prime divisor, then there exists a subgroup of order P. Okay, so that's the statement. So you might have seen in one of my problem sets. So mind that my problem set is very interesting. So as I always mention that this problem set consists of problems from around 2001 to very current problem sets that usually comes in varieties competitive exams starting from TIFR to NET, NBHM, GATE and all. Okay, so at this point of time you may not be able to solve all the problems. So when you will be at your higher studies, maybe at when you will be in undergraduate level of UG 3, that means third year of undergraduate level, then you will find that more problems that you are able to solve, because more tricks that you will able to come to know. But remember, this problem set will be helpful till your MSc. I mean, at the end of your MSc, when you are going for NET, GATE, NBHM, TIFR exam, then also you will find that problem set very useful. Okay, so in one of the problems might be like this. Suppose order of a group is even. Okay, and then you need to prove that there exists an element of order 2. Suppose G is a group of even order, then what you need to show, there exists an element of order 2. So if you use Cauchy's theorem, then your statement is, then the proof is just simple, very one-line proof. So by Cauchy's theorem, since this is even, so 2 is a prime factor of order of G. So 2 divides order of G. That implies G has a subgroup of order 2. And within that subgroup, so order 2 means it must be cyclic. The subgroup must be cyclic since this is of prime order. So the generator of the cyclic group must be of order 2. So that implies G contains of order 2. And this problem can also be solved in a different way, but if you use Cauchy's theorem, then the proof is very easy. Otherwise, you need to use some tricks, collection of even, odd, etc. And then by using some techniques or some argument, you will at the end, you will end up with the fact that there must exist an element of even order or order 2. But with Cauchy's theorem, the statement is one line proof. Okay. So in our syllabus, for this time being, since you are at the undergraduate level first year, what we need to have, the statement is, that is also very simple. The statement is for a finite commutative group. So it's a modified statement of original Cauchy's theorem. It's a simplified statement, or maybe at the very basic step, you need to prove this and then you need to prove Cauchy's theorem. It says that let G be a group of order n, but G now is of special type. G is commutative. So note that in case of Cauchy's theorem, the commutativity property was not assumed. It was any finite group whose order was n. So now I started with G. So here I can mention it should be a commutative group of order n, but I just want to make it highlighted. That's why I made it in that way. So I started with the formal like any group, but then to make you understand that we are not talking about any group, but we are talking about a finite group. So sorry, a commutative group. Okay, abelian group. So let G be a commutative group or abelian group of order n. Let P divides n, then there exists a subgroup of order P, or in other way, there exists an element of G having order P. Note that it is sufficient to have this subgroup or this element. They are equivalent. So if you have this element, then consider suppose A is an element of order P, then consider the subgroup generated by A, then that subgroup will have order P. So if order of A is P, then the subgroup generated by A will have the order P. On the other hand, if you have a order P subgroup, since P is prime, as a result, the subgroup that is of order P must be a cyclic group. If it is cyclic, then it must have some generator. Suppose this is my generator, then the order of this generator will also be P, same as the group. Okay, so both the statements are equivalent. Now, anybody be able to give me any hints or something? Any idea? Okay, just I will follow a very standard textbook argument. It's already given in a book. So it says that let G be a finite commutative group of order n such that n is divisible by a prime P. Then G contains an element of order P, hence a subgroup of order P. The same thing. Okay. It starts with the principle of mathematical induction. So you can start with, so what is where you are going to use? You are going to use the principle of mathematical induction on order of G. Okay. Now, for order of G, it must have some starting point. So you cannot start with order of G equal to 1 because P has to divide, some prime has to divide the order of the group. So the order of the group must be at least 2. So let's start with order of G equal to 2. In that case, what you will have? So in that case, so G must be, thus in particular, take a lemma is true for order of G equal to 2. Now make the induction hypothesis that the lemma is true for, okay. So if order of G equal to 2, what is your claim? So prime P divides order of G. So here, which is the prime? It must be 2. So 2 divides order of the G, and G is order 2. So G must be isomorphic to Z2, right? A cyclic group of order 2. Since this is a cyclic group of order 2, it must have a generator whose order is, say, A is a generator, then order of A must be equal to 2. So you prove that there exists an element of G whose order is 2 and the element whose order is also 2. So if 2 divides order of G, then G contains an element of order 2. So we are done basically for 2 case. If the order of G is 2, then we are done. So now we want to use the strong statement of mathematical induction. What it says: now make the induction hypothesis that the lemma is true for all groups of order R, where it's within a range. That means you consider the result is true for all groups of order R such that R varies over n. So now the induction step will be take a group of order n. So within that range, if the order of the group is within that range, then the lemma is true. What is that lemma? Lemma says that if some p divides the order of the group, then there must exist some element of that order. That's all. Now we assume a group of bigger size. So it was group, the result was satisfied for strictly less than n. Now I consider a group whose order is exactly n. Okay. Now we are going to prove the result, this statement for order of n. Okay, or for the group whose order is n. Okay. Now take an element A belongs to G such that A not equal to E. So order of A must be there. Let order of A equal to M. Okay. Now two things may happen. Either P divides M or P does not divide M. Note that order of A is M. Okay. If P divides M, then M must be of this form, P into some constant K integer for some positive integer K, not constant, I mean for some positive integer K. So this is positive, this is, both of them are positive, so K must be some positive integer K. In this case, A to the power K to the power P, what is this value? A to the power Pk. And what is this value? A to the power Pk equal to M. And what is the order of A is E. Okay. That means, now what would be your conclusion? Can anybody tell me what would be the conclusion? You can see this. What would be your conclusion? So A to the power Kp is equal to E. Okay. And can it happen that A to the power K equal to E? Can it happen that A to the power K equal to E? If that would happen, then what would be the contradiction? Then what would be the contradiction? Will that happen?
M divides K, that will be
N divides K. Will that happen?
that will be a contradiction, I think.
Yes, that is my question. What would be the contradiction? If
M
this,
cannot divide K. If P is
M cannot divide K. If that is true, yes, you are right. If that is true, then what would be your conclusion? Because you know that A to the power M equal to E, because that's the order. That's why A to
then
the power M equal to E. And this is the smallest positive integer for which a to the power m equal to e. No integer which is less than m can make it e. If a to the power k equal to e, then what will be your conclusion? Since a not equal to e, note that it is there already, assume that a not equal to e, then what would be your conclusion? If a to the power k equal to e, that means m must divide k. Okay, then what would be the problem? If can't be this, both p and k are positive integer, p is a prime number, and then what would
Then
be your,
P will be 1. P will be 1, and that is.
and then p will be 1. So you will get some contradiction. Okay, so it follows that a to the power k can never be equal to e. But a to the power k to the power p equal to e. Then can anybody tell me what would be the order of a to the power k then? What would, it has to be p, because p is a prime number. Okay, it cannot be anything between, it can be either 1 or p, but a to the power k is not equal to e, but a to the power kp equal to e. So order of a to the power k must be equal to p, and that is your element. That's what you are searching for. You are actually searching for an element whose order is p, and a to the power k is that element whose order is p, right? So that was your claim, that if p divides the order of the group, then there exists, contains some element of order p. So we have found an element a to the power k whose order is p, but the proof is not yet done. It's only done for the case when p divides m. So there is another part when p does not divide m. Okay, so let's have a look at what happens here. Now suppose p does not divide m, the other case. Since G is commutative, here the commutative property is playing the role. The cyclic subgroup H generated by A of G is of course a normal subgroup of G. Okay, so you started with G, you take an element which is not an identity element. Since this is commutative, every subgroup of G is also a normal subgroup of G. So you must have this quotient operation. So this will also form a group, right? So G is there, a normal subgroup is there. Again, I am repeating, since G is commutative, the cyclic subgroup, which we denote it by H of G, is of course a normal subgroup of G. Now, order of G equal to m into this. Why this is so? What is the order of H? What is the order of H? Can anybody tell me what is the order of H? So this is generated by A, and we have already assumed that order of A is m, and then two cases arises, right? So order of A is already m, so order of H is m. All of them are finite group. So order of G, what is that? Order of G divided by order of H, and that is nothing but the index. So order of G equal to, what is this value? Order of H was m. So m into G quotient H. So that's written here. Since P does not divide m, we must have P must divide whom? P divides order of the group. That was hypothesis. And P does not divide m. So P must divide this. That's what written here. Since P does not divide m, we must have P must divide this one. So P must divide G index H. Now, see, m is not equal to 1 because it is generated by a, which is not equal to e. So the value of, so a not equal to e, that means order of m must be strictly 1. Okay, so order of or index of g, or you can see that order of g quotient h must be strictly less than order of n, because you are dividing with some number which is greater than 1, because this is same as order of g divided by order of h. So this number is strictly less than n. Remember what was our induction hypothesis. So G was a commutative group, H was a normal subgroup. As a result, G quotient H is a group whose order is strictly less than n. Now remember about the hypothesis. What was our hypothesis? Our hypothesis was, make the induction hypothesis that the lemma is true for all groups of order R where 2 less than R strictly less than n. That means the result, the lemma is true for all groups whose order is strictly less than n. So we have found a group here whose order is strictly less than n. Okay. That's why we can apply induction hypothesis. So then we, by induction hypothesis, there exists some element of whom? Of G quotient H. Now how the element of G quotient H looks like? Some GH type. What the induction hypothesis says that if the result is true, that means if P divides the order of the group, then there must exist some element of G. Now instead of G we have G quotient H. So there must exist some element GH of G quotient H such that order of, so here it says BH. Okay, let me follow the rule of the book, must be equal to P. So there must exist some element of this group whose order is P. So this is the element. Now BH to the power P, what is this value? This must be the identity element because this order is P. And what is that identity element? H. H is the identity element of G quotient H. Okay. So what does it mean? B to the power PH equal to EH. Okay. So let me just write it down. I just erase it a bit. Okay. So B to the power PH equal to EH. What does it mean? Then B to the power P into E inverse. So you understand the result. E inverse B to the power P must be belongs to H, and E inverse is E. So this belongs to H. Okay. That's, you can see that is belongs to H. Yielding B to the power P belongs to H. Thus, what is the order of H? Okay, what is the order of H? You remember what is the order of H? See that the order of H is M. Now B to the power M to the power P equal to B to the power P to the power M equal to E. Why it's so? Because PM, why it's so? Because order of H is M. So if you put anything, any element, so B to the power P was within H. So B to the power P to the power M must be E because the order is M. And B to the power P belongs to H. So B to the power P to the power M must be equal to E, and that is same as B to the power M P. Okay. So that's it's saying. yielding that. Now what is the contradiction then? If that is the case, then what is your conclusion? So b to the power p or b to the power, so it might have two cases. See, b to the power mp e, so that either b to the power m equal to e or b to the power m has order p. So it has two cases. So we have already proven that b to the power mp equal to b to the power p to the power m equal to e. So now we have two cases. Either b to the power m equal to e, that implies either b to the power m equal to e, or b to the power m has order p. Okay. So you are considering b to the power m. B to the power m. So just now we have mentioned that either this is e and this is prime. So either this is e or the whole thing, it has order p. Okay, there cannot be anything in between because p is a prime number. Okay, but b to the power m not equal to e. Why b to the power m not equal to e? Why b to the power m not equal to e? Anybody? Why b to the power m not equal to e? See, what was our, we started with two cases, right? One is p divides m and p does not divide m. Now tell me what b to the power m is not equal to e. Then what will happen? If b to the power m not equal, if b to the power m equal to e, then what will happen? What will happen? Anybody? Are you listening? Okay, just go step by step. Everything is written over there. So here the concept is very much given. So if this happens, if b to the power m equal to e, what will happen? Then this value becomes e, h. So this is the identity element yielding p divides m. And that is a contradiction because we started with this case. We started with the case when p does not divide m, and that arises due to the fact that if we assume that b to the power m equal to e, if we assume b to the power m equal to e, then that will happen and that will be a contradiction that p divides m, which is not possible. That's why b to the power m has order p. And so we get an element b to the power m of the group whose order is p. So we are done. It might happen that it may look little complicated to you because not yet you have done any serious theorem, but it is, that's why it's a little complicated one. It requires little tricks, few cases, sub cases, but just believe me, it's not that difficult. You just make a screenshot of this result. You just take a screenshot of this result and you just do step by step. Everything is very easy. Not very deep results are being used. Only thing is that what is the definition of order? If order of some element is something, then what it happens and how it is helpful in proving that, and the induction hypothesis that are being used here, nothing else. And the proof is, rest is very simple. Okay, good. So any question? Any question? Okay, if not, then we'll come to almost arrive to our final goal, and that is known as Sylow's theorem. Sylow theorem. And Sylow has given 3 theorems. Many books, sometimes it's given in one form and sometimes it's given differently. Okay. So what is the statement? The statement is, let for a finite group, let G be a group of order n and let P divides n. Okay. Where P is a prime number. Where P is a prime number. Then see one thing, if P divides n, then you can always write, then we can write order of G equal to n equal to in this form, say P to the power R into M, such that GCD of P and M equal to 1 and R greater than equal to 1. Okay, looking at this, you may think that it's very complicated, but believe me, I'll just give you an example, then you will understand that this statement is obvious. Okay, for example, suppose order of G is say 96. Okay, so what we know that 2 divides 96. Okay, now this statement means, so here 2 is my P, so P divides 96. This statement means you just take out as much as you can the portion of 2 from 96. So you can write it like this, 2, if you write it like this, 2 into then 48. Still you can take it out, 2 square into 24. Still you can take it out, 2 cube into 12. Still you can take it out, 2 to the power 4 into 6. Still you can take it out, 2 to the power 5 into 3. Now you cannot take it out. So what is 2 to the power 5? 2, 4, 8, 16, 32. And 32 into 3. That means it's like a kind of injection. You are actually extracting, say, 2 portion from 96 through some injection. You have taken some portion out and then you see that some extra portion of 2 is still present within that 96 part. So this is the remaining part, or you can say the extra part of 96 after taking 2 out. Again you take it out, take it out, take it out, take it out. But after that you cannot take it out any 2 portion from here. Why? Because the GCD of M and P is 1. That's why you cannot take anything out. That's why the GCD of P and M is 1. And see, R is greater than equal to 1. If you can see that R may be greater than equal to 0, but then you can take from any number to any number. For example, you say 96, you can think about P to be 7. Now you can very well write that, okay, why not 7 to the power 0 into 96, then you see that GCD of 7 and 96 equal to 1. So you are done basically. But that is not a case. So if you consider, if you allow R to be 0, then any prime is sufficient here. But since we are considering R to be greater than equal to 1, as a result, the significance presence of P must be there. Okay. Now this portion is clear. It's very easy. Okay. So quickly, can you tell me what is say 46 and P is 2? Can quickly tell me how should I write it? 46 equal to, in terms of 2 to the power 1 into 23. So this is my M, this is my P, and this is my R. And that's all. If you are able to write in that form, then you are basically done 50% of Sylow's theorem. Okay, so that part looks little complicated, but this is very easy. Okay, then 3 theorems are there. Okay, let me write it here. Three theorems. Theorem 1, Sylow theorem. Okay, so initial stage is let order of G equal to n equal to p to the power r into m, where p is a prime, GCD of p and m equal to 1, and r is greater than equal to 1. So all these things are very important. Prime, GCD PM equal to 1, and r is greater than equal to 1. That is also important. Otherwise, you can understand, you can do it any prime. Then theorem 1, and that is Sylow theorem 1. There exists a subgroup H of order p to the power I, and it runs over 0 less than equal to I less than equal to r. It's very important result. What it says, again, try to look at converse of Lagrange's theorem. Converse of Lagrange's theorem in case of, say, order of G equal to 92. So 90, what I told, 98, I guess. 98. So how many positive divisors are there? Now quickly tell me how many positive divisors are there. That means tau of 98, how much? Quickly. Tau of 2 to the power, how much it was? 5. Tau of 2 to tau of 3. What is tau of? This is how much? Tau of 5 is 2 to the power 5 is how much? Quickly, quickly, tell me.
So 98 2 to the power 5.
Okay, what I did, 96 was, okay, oh, sorry, it was 96. Yeah, so 96. Just now I did, right? What I did? 96 I did, no? Okay, so let me again do this. It was 96, right? Just now what I did? Okay, so let us the converse of Lagrange's theorem for order of G to be 96. 48, yes. So what I did,
Six.
what I did, 90. In my example, what I did, yeah, so it was 96, right? And 3 into 32, yeah, it was done. So it was 96. Okay. Yeah, so here. Okay. So let us consider the converse of Lagrange's theorem for order of G equal to 96, and that was 96. Then the number of positive divisors of 96 equal to tau of 96, and this is how much? Tau of
12.
5 into tau of 3, and that is 6 into how much? 2, and that is 12. Quickly tell me, who are the positive divisors?
1, 2, 4,
4,
8,
8,
16, 32,
16, 32,
and 3.
3. Anything else? Then
No.
6. No, 6 will also
Oh,
be
6.
there.
Sorry.
So you have already 12, but here are 1, 2, 3, 4, 5, 6, 7, 8. 4 more. Tell me, who are they? Then 12. Multiply 3 with this. Yes, 24, 48, and then 96. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they are all the positive divisors. If the converse of Lagrange's theorem would hold, then there must exist a subgroup of each of this, right? Okay. But what the Sylow theorem says, it's not exactly the converse. Note that I am not considering about any finite abelian group or finite cyclic group, any group of order 96. Then it says that there exists a subgroup H of order p to the power I, where I varies over this. That means there exist actually r plus 1 subgroups of that order. What it says, if I consider p to be 2, then it says that there exists a subgroup of order H whose order will be 1, that means p to the power 0, that means 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. That means 1, 2, 4, 8, 16, 32. That means you see that all this which were there in converse of Lagrange's theorem are now being guaranteed by Sylow's first theorem. So if you take P to be 3, then you will have, then you can also write in that way 96. Then you can write 96 as 3 into 2 to the power 5, that means 2 to the power 5, 32. So this will be your M. 3 to the power 1, this will be your R, and this will be your P. So the Lagrange's theorem will say that there exists a subgroup of order p to the power I, 0 less than equal to I less than equal to 1. That means you will have a subgroup H whose order will be either 3 to the power 0 or 3 to the power 1. That means this is 1, 3. So you will also achieve this. So now you can understand that why the partial converse of Lagrange's theorem is true. In case of Cauchy, it will only guarantee these two. In case of Cauchy, 2 divides 96, 3 divides 96. So according to Cauchy, there exists a subgroup of order this and this. But if we have to be full converse of Lagrange's theorem, for each positive integers, there must exist some subgroup. But Sylow gave you much generalization, which is also covering these two. That means Sylow theorem is a generalization of Cauchy's theorem itself. And it says that it's not only this 2 and 3, but it also gives you 1, 4, 8, 16, 32, and 3 and 2 all. But it cannot give you any guarantee about the existence of a subgroup of this order. Note that we are now considering any arbitrary group. It may be non-commutative group as well. Okay, but whatever be the group, Sylow theorem guarantees you the existence of these many subgroups. Is it clear? The first theorem statement is clear to all of you? Okay. Then the statement of second theorem. What it says? It says that any two. Okay. So before that, let me define what do you mean by Sylow subgroup. Sylow P subgroup. That's very easy. So you have seen that in case of P, what is the maximum value of P to the power I? What is the maximum value of P to the power I here? What is the maximum value of p to the power I? Is, quickly tell me, maximum value of p to the power I? Quickly. How much? P to the power? Quickly. How much? P to the power? You can see this. What is the maximum value of p to the power I?
R.
So
Yes, very good. So you can see that the maximum value of p to the power I is p to the power R. And there exists a subgroup of p to the power R as well. You can see that there exists a subgroup of order 32. If you p considered to be 3, then the maximum order of that subgroup will be 3 to the power 1, which is 3. So there exists a subgroup H whose order is p to the power R. And that subgroup is known as Sylow P subgroup. P subgroup. That means the subgroup whose order is maximum in terms of P. So Sylow P groups. That means in case of 96, the order of Sylow 2 subgroup is how much? Quickly. In case of 96, what is the order of Sylow 2 subgroup?
32.
32. So the maximum order of among all this, P's maximum power. P's maximum power will be the subgroup corresponding to the maximal power of subgroup. It may happen that there may exist many such subgroups. It is not unique. What it says, there exists a subgroup. It may happen that that subgroup is unique. It may happen that that subgroup is not unique. Okay. Now the second theorem states that any two Sylow subgroup, Sylow 2, any two Sylow P subgroup are conjugate. So you have any idea about what do you mean by a conjugate subgroup? When two subgroups H and K are said to be conjugate, any idea? Are conjugate if there exists some H or say G, whatever, G belongs to G such that GH G inverse equal to K. If there exists some G belongs to G for which this property is satisfied, then we called these two subgroups H and K are conjugate. What the Sylow's second theorem says, it says that any two Sylow 2 subgroups are conjugate. Okay, and a very important consequence from here is that suppose there exists only one Sylow P subgroup. Suppose there exists only one Sylow P subgroup of order p to the power R. There exists only Sylow P subgroup, say H. Then what can you say anything? Can you tell anything about H? Any conclusion about H? In that case, what will happen? Only one subgroup. That means H is conjugate with itself. That means GH G inverse equal to H. Okay. Then what is your conclusion? So that is true for all G belongs to G. Then what will be your conclusion? Anything, any special property that GH will satisfy?
Normal subgroup.
That implies H is a very good. H is a normal subgroup of G. Normal subgroup of G. That means if there exists only one Sylow P subgroup, then that subgroup must be a normal subgroup. That's also very important. And the third one, and that is most important for doing the problem, theorem 3, it says that the number of Sylow subgroup, the number of Sylow P subgroup is the number denoted by NP is given by NP equal to K into P plus 1, where NP divides the order of the group. And that result is very important for doing the problems. What it says that the number of Sylow P subgroups. So just now I have mentioned that existence of Sylow P subgroups are there from the first theorem, but it may happen that for a particular group there exist many Sylow P subgroups. But just now in theorem it says that any two Sylow P subgroups are conjugate, so they may be conjugate. But the point is the number of Sylow P subgroup, how to calculate. This formula actually give you the calculation. If NP denotes the number of Sylow P subgroup, then the form of NP is of this form, some Kp plus 1, where 0 less than equal to K, okay, where K equal to 0, 1, 2. So K may vary from anything, but you can understand that after some time it will cross. If you increase K, then after some time NP value will exceed order of G. As a result, after some time you have to stop. Clear? So number of Sylow P subgroup is basically given by this formula. Is it clear to all of you? So this is the statement for, I am not giving you the proof of this results because the proofs requires, there are many ways to prove this. One of the ways to prove this is by group action, but not yet you have studied group action. In your third year level, you will study this group action. But you will able to prove many results. For example, any group of order 15 is cyclic. It's very easy to prove now. Any group of order 15 is cyclic. You can prove that. So 15 is 3 into 5. So you can write it 3 to the power 1 into 5. So there exists Sylow 3 subgroup, Sylow 5 subgroup. Now try to find how is the N3, that means number of Sylow 3 subgroups. It must be of the form 3K plus 1. So P is my 3, and it also divide 15, right? So you need to check for which values of this K this satisfies. You can always see that if K equal to 0, then this N3 value is 1. So in that case, N3 will be equal to 1, and that will always divide 15. So if K equal to 0, then N3 equal to 1. But if you put K equal to 1, then this value is 4. So 4 cannot divide 15. If you put K value to be 2, then 7 cannot divide 15. If you put K value to be 3, then 9 plus 10 cannot divide 15, and so on. You will find that only K value to be 0 gives you N3 value is 1. That means the number of Sylow 3 subgroup is exactly 1. Similarly, you can prove that the number of Sylow 5 subgroup is also 1. Just now in second Sylow theorem, we proved that if there exists only one Sylow 3 subgroup, then it must be a normal subgroup. So suppose H is that normal subgroup. Similarly, if that is the case, then K is the only Sylow 5 subgroup. So order of H is equal to 3, order of K equal to 5. So you found that there exist two subgroups, exactly two subgroups whose order is 3 and order is 5, right? Now try to find what is the order of HK. We have already seen this formula is order of H divided by order of K divided by order of H intersection K. Now tell me what is the order of H intersection K. So order of H intersection K must divide both order of H and order of K. And So it must divide the both 3 and 5. And what is that number which divides both 3 and 5? It must be 1. So it must be order of h is 3 and order of k is 15 divided by 1. That, sorry, 5 divided by 1. So this is order of 15. So hk is a subset of G. This order is 15, this order is also 15. So what is your conclusion? G must be equal to hk. Okay. So there is one result which you may not know. In that case, since both of them are normal subgroups and G equal to hk, then you can suddenly write this is isomorphic to H cross K. So this is of order 3, this is of order 5. So this must be isomorphic to Z3 cross Z5. Since both of them are relatively prime, so that must be isomorphic to Z15. So you started with any arbitrary group of order 15, and ultimately you end up with the fact that the form of G must be this. So G must be isomorphic to Z15. So whatever may be the group, if its order is 15, it has to be a cyclic group. That's very important. And there are plenty of questions are being asked in the every competitive exam from Sylow's theorem. Okay, so this part is very important. But in our syllabus, we had only the statement. Okay, so now I will just come to the history of this group, as I just mentioned. So now I covered all the things: Lagrange's theorem, abelian group, normal subgroup, Cayley's theorem, Cauchy's theorem, etc. And note that the definition of group actually came during this time, 1870 or 18 after 1870 or after 1882 by Jordan and Dirac. Now see, if I ask you the question, who invented Lagrange's theorem? If your answer is Lagrange's gave the Lagrange's theorem, then you are certainly wrong, because Lagrange's was there from 1736 to 1813. So much before the formal definition of group, Lagrange's actually died. So Lagrange's had no clue about the axiometric definition of group theory. So then how he gave the theorem like Lagrange's theorem? Similarly, if you look at Abel, he was there with us from 1802 to 1829, very small span, only around 26 years. But within that, he did a lot of things. And still you can see that he died much before the formal definition, axiometric definition of group, 1870. Usually what we assume that normal subgroup, that is actually, or the term group actually, that is coined by the, again, of genius, Galois. And his span was 1811 to 1832. So around 20 years. So at the age of 20, he died. I will give you a very brief sketch about all of them. You will be able to understand how big or how great mathematician he was. So again, this definition was much early than the formal definition of Galois. Then he didn't have any idea about group. Then how can he give the definition of a normal subgroup? Similarly for Abel, we know that what do you mean by a commutative group or abelian group, but Abel didn't have any idea about that group, concept of group. Similarly, Cauchy, Cauchy's theorem, he proposed it 1846. Cauchy's theorem today we have proved. Similarly, Cayley's theorem was also proved around 1854. So much before than the formal axiometric definition of group theory, what we study today, what you study today. So you understand that none of the great mathematicians, they actually knew the definition of the group theory, formal definition, axiometric definition of group theory, but how this name came after their name. So that's quite interesting. Okay, so if you have a look at this Lagrange's, so we are studying basically this Lagrange's theorem, but if you look at Lagrange, so Lagrange was really a mathematician, great mathematician, but you'll be surprised to know that this French mathematician did not show any interest for mathematics until he was 17 years old, quite aged till he did not had any interest on mathematics. from his 17, he alone threw himself into mathematical studies. So for you, what I say that it's not too late even to do some big work. So you can also do like what Lagrange did. Already at 19, he wrote a letter to Euler in which he solved the isoperimetrical problem, which was for more than half a century had been a subject of discussion. So it was at that time it was a hot topic, and he wrote a letter and he solved that problem at the age of 19. Just see, at the age of 17 he started working. I mean, he started thinking about mathematics seriously, and at the age of 19 he did a great job. He worked on a problem of analytical geometry, algebra, theory of numbers, differential equation, mechanics, astronomy, and many others. Now, the interesting portion comes into picture. Okay, the Lagrange's theorem. Okay, before that, again, an interesting topic. So, in my last class, I talked about Wilson's theorem, and you will be shocked to know that Lagrange was the first person who proved Wilson's theorem. It was not Wilson who proved the Wilson's theorem, but it was Lagrange who proved the Wilson's theorem. So what was the exact history about Wilson's theorem? This theorem was stated by Ibn al-Haytham around 100 AD, 1000 AD, and in the 18th century by John Wilson. So Wilson only stated, so actually Edward Waring announced the theorem in 1770. Note that 1770, he was his teacher, he announced the theorem, although neither he nor his student Wilson could prove it. That means they only announced the theorem, but it was Lagrange who gave the first proof in just after 1 year when it was announced. The problem was announced. Okay, so again, a quite interesting history that Wilson's theorem was not given by, the proof of Wilson's theorem is not done by Wilson itself, but it was by Lagrange. Now have a look at this history about Lagrange's theorem. So the statement we all know. Now, the interesting fact is that Lagrange did not prove Lagrange's theorem in its general form, that is this form, because he didn't have any idea about what do you mean by a group. Okay, he stated that if a polynomial in n variables has its variables permuted in all n factorial ways, the number of different polynomials that are obtained is always a factor of n factorial. Okay, so what do you mean by that? He stated that suppose you have a polynomial, of say, let's see, yeah, suppose you have a polynomial say of 3 variables, say fx equal to say x1 square plus x2 x3. So it's a 3 variable polynomials. So there are 3 elements. So how many permutations that you can have on 3 elements? 3 factorial, right? So let us write it down. So E, so 1 2 3, 1 3 2, 1 2, 1 3, 2 3. Okay, so if we apply E on it, that means x1 remains to x1, x2 remains to x2, x3 remains to x3. That means the polynomial remains the same. If I apply this, then 1 goes to 2, that means x1 goes to x2. So x2 square plus 2 goes to 3, x2 becomes x3, and x3 becomes x1. See, this and this polynomial are different, not equal, right? Now for this, what we'll have, 1 goes to 3, that means x3 square plus 2 goes to 1, 2 goes to 1, that means x1 into x2, 3 goes to 2. Okay, again you see that this is not same as this. Now what happened for 1 2? So x1 goes to x2, that means x2 square plus 2 goes to 1, that means x1 into x3 remains x3. Now can you find any similarity between any of them? Yes, they are similar, right? So I just put it in black. So this and this, they are the same polynomial. Now for 1, 3. So 1 goes to 3 means x3 squared plus 2 goes to 2. So x2, 3 goes to 1, x1. And for this, x1 goes to x1 plus 2 goes to 3. That means x3 and x2. Let's have a look at which are the similar one. So x3, x3. So this and this, that is similar. And this one and this one, you see that similar. Okay. So though we have polynomials with 3 variables, but all the 6 many permutations will actually give rise to 3 different polynomials. 3 different polynomials. Okay. Out of which you see that which permutation or which permutation group actually keeps this polynomial same. That means this polynomial and this polynomial are same. And you see that if you consider a subgroup H, which is generated by E and 2, 3, then this polynomial becomes the same polynomial. If you associate with this subgroup with this polynomial, then this subgroup induces the same polynomial. That means this polynomial remains invariant under this subgroup because this and this are the same. And if I consider 2 elements, we see that this forms a subgroup. Okay. Now let's come to the again statement. Now it will be quite clear. He stated that if a polynomial in n variables has its variable permuted in all n factorial ways, so 3 variables permuted in 6 ways, the number of different polynomials that are obtained. So here we obtain 3 polynomials is always a factor of 3 factorial. That means 6 factorial. So we get 3 different polynomials. So 3 divides 3 factorial, that means 6. Okay, now you will be able to understand how it is associated with the Lagrange's theorem. So the number of such polynomials is the index in the symmetric group Sn of the subgroup H of permutation that preserves this polynomial. So you can understand that here H is E23. So this is a subgroup, and in S3, what is the index of this? This is equal to, basically, since this is a finite group, this, and this is 6 divided by 2, and this is 3. So this index is same as the number of 3 distinct polynomials. The number of such polynomials is the index in the symmetric group Sn of the subgroup H of permutations that preserves the polynomial. So H is the subgroup which preserves the polynomial, and this 3 value, which is nothing but the index of H in S3, this is same as the number of different polynomials that are obtained. So that was the statement given by Lagrange's. Okay. Now, so Lagrange's actually give a particular case of the whole group in case of Sn. But remember, he was actually not, he didn't had any idea about index or all. He actually worked on only polynomials with n variables. Now later on, Gauss, again another big mathematician, proved Lagrange's theorem for a special case of ZP star. So you understand, in number theory, ZP star is same as UP, the group of units, and Gauss actually proved the result as a particular case of Lagrange's theorem where the group was ZP star. Then Cauchy also proved Lagrange's theorem for the symmetric group Sn. Okay, and ultimately Jordan finally proved Lagrange's theorem in case of any permutation group in 1861. Okay, and it was Jordan who actually gave the name Lagrange's theorem to give an honor to Lagrange's. So it was finally, the name was given by Jordan, who actually proved at an final stage, and when he was searching that who actually started working on it, and he found that history, and he was really a genuine gentleman, and he finally gave the name after his name, Lagrange's theorem. Okay, so if we consider again this Abel, so just now I have mentioned that Abel died at the age of around 26. So he was again the proof. He proved actually again a great theorem that was open problem for more than 350 years. So the problem statement looks like this. So if I ask you a question, can you give me a solution for x plus a equal to 0? You will say that okay, x equal to minus a. If I ask you the question, can you give the solution for like this, x square plus ax plus b equal to 0? You will use Sridharacharya formula. If I give you x cube plus ax square plus bx plus c equal to 0, or maybe x to the power 4 plus ax to the x cube plus bx square plus cx plus d equal to 0. So you can understand that this is degree 3, degree 4. Okay. If I also give you, you can apply Cardan or Ferrari methods to give the solution of this equation. But if I ask you a question, can you give the similar formula? So you know what is Sridharacharya formula. So it uses basically the radicals method. Okay, they also use some radical methods. But if I ask you the question, if a polynomial is of the form whose degree is greater than equal to 5, up to 4 is fine, but what will happen if the degree of the polynomial is greater than equal to 5, and can you solve any polynomial of this form? See, they are the arbitrary form, right? So depending on, so it can also be there something, some maybe some capital A is also there. So that is the complete general form of the polynomial of degree 3 or 4, right? So starting with any polynomial of that degree greater than equal to 5, and if I ask you the question, can you give some kind of similar formula like this, then what will happen? If I ask you to solve this, then it will be very easy. Say if x to the power x minus this is 5. You know that x equal to 5, and there are 6 such roots. But it does not mean that it will always give me the result if fx is any arbitrary form. Okay, so the question is, what will happen? Can we find some method for arbitrary form of fx if the degree is greater than equal to 5 by using this radical methods? That means using some square root minus b plus minus a square minus 4a b square minus 4ac by 2a something. Can I have this kind of formula for any polynomial of whose degree is greater than equal to 5? The answer, if something's answer is yes, then it somebody may try to do so, but his answer is no. And Abel and Galois, they independently prove this. And one of the very important consequence between them is that both of them, they died at a very early age. One at the age of around 20, another one at the age of around 26. But independently, both of them, they prove this result that it cannot be possible, which was unsolved for at that time around 350 years. So he discovered many other things and so on. So Abel was unrecognized. So the most pathetic part is that Abel was unrecognized during his lifetime, made his discoveries while living in poverty. So he was a very poor guy, and he died at the age of 26. You can Google and you can check all the details about it. Afterwards, those who might have heard about Lie algebra, Lie groups, that he was again a mathematician from Norway. So you can see that Abel was also a person from Norway. So afterwards, when Sophus Lie, he was trying to understand the work of this Abel, he was surprised, and he actually proposed in 1899 that the Abel Prize in Mathematics. So he proposed this Abel Prize in Mathematics by when he learned about Nobels. So you know that Nobel, Alfred Nobel, who actually is the father for this Nobel Prize, and in mathematics there is no Nobel Prize. So that's quite surprising. So there are many reasons that people they think, okay, I'm not sure which one is the correct one, but the actual fact is that Nobel did not give any prize amount to the mathematician. But when Lee came to know that there is no prize for mathematicians in Nobel, which is yearly done, then Lee actually proposed it in 1899 that there should be some Abel Prize. But it was a long history and it took more than 100 years to settle down, and finally it was given by Swedish government and the Norway government together to Salzburg. The first Abel Prize, it was given in honorary prize in 2002, but the actual prize was actually awarded in 2003. So after a long time. Okay. So if you look at this, again, Abelian group were named after Norwegian mathematician this by Jordan. Again, Jordan gave the name Abel after the name of Abel when he found that similar kind of thing when he was actually Abel found that the commutativity of the group of a polynomial implies that the roots of the polynomial can be calculated by using radicals. Okay, so he proved that in terms of polynomial groups, but he didn't have any formal idea about what is group. That's why Jordan finally gave the name Abel after his name, that Abelian group. Now he is one of the again most genius mathematician in the history of mathematics. He was Galois. He was again a French mathematician. Okay, so if you Google it, you will able to learn many things about this. So at the beginning, he didn't have any formal education. So his parents they decided to send him to a not send him to school, but then he started learning things at his home. In 1823, Galois entered to the Louis Grant in Paris. So I had an opportunity to visit all of the great mathematician in France because many of them they stayed at that time in Paris. So I spent my nice life in Paris for 1 year around for my postdoc, and I had the opportunity to visit all those places. So then you can understand that how when you learn something or you read something about someone, and then when you go to that place, then it's really amazing. I cannot express myself how amazing it was. Okay, so Galois actually performed not that well, but he became bored with his studies at the age of 14. Okay, and he began to take serious interest in mathematics. So at the initial stage he was not that interested, but at the age of 14 he became again interested on mathematics. So this is École Polytechnique and École Normale Supérieure. So they are one of the two big names in terms of institutes in Paris. Okay, so in 1828 he attempted the entrance exam of École Polytechnique, but failed for the lack of explanation on the oral examination. So it might happen, what I can think of, that what he answered is beyond the understanding of the judges that were there at that time. Might happen, but don't underestimate the judges. So I will give you a few names there, then you will understand that who were maybe the judges or what could be the capability of the examiners who took the examination of Galois. But anyway, at the same year he entered the École Normale. So it's again a very prestigious institute in Paris. But he was politically motivated. So just understand, he was just an age of 20, he did a lot of things. He died at the age of 20, but within that he was politically motivated. Galois have been interested in politics when he was still attending the school. So that's the school name. But his political activities started namely at École Normale. So in This year he joined Ecole Normale as a student, while their counterpart, so remember the timing, so that was around 1830, and you can understand that during that time it was a kind of we call it French Revolution. In the month of July, we all know that it's a French Revolution time. So at that time he was a student of that Ecole Normale. So while their counterparts at Polytechnic were making history in the streets during that time, Galois and all the other students at the Ecole Normale were locked by the school's director. So the school at that time, it was a revolution. Okay, so everybody, especially the young students, they are actually demonstrating on the roads. But unfortunately, during that time, Galois and his friends from Ecole Normale, they were locked by the director at the school. Galois was expelled from school on 9th December, publicly announced on 4th January because of an announcement letter to the Gazette des Écoles. That means some notice board or something, where he sent some anonymous letter that his letter that the director was blamed for his behavior during the July French Revolution 1830. That means he actually sent some letter, anonymous letter, and he published it in the Gazette of Ecoles, saying or blaming that the director of that institute didn't do proper justice with the students by locking them or by making them confined within that campus. That's why he was expelled. Then after doing that explanation, he actually he constantly studied mathematics, and he attempted to start a private class in advanced algebra. You heard about Poisson. Poisson asked Galois to submit his work on the theory of equations. Poisson declared Galois' work this, declaring that Galois' argument is neither sufficient, not clear, not sufficiently developed to allow us to judge his rigor. That means Poisson actually started, so he submitted his kind of paper or thesis work to Poisson. He was again a great mathematician, and then Poisson couldn't understand it, and he says that with less rigor or less uh, proper argument is not given. That's why he told that he would then suggest that the author should publish the whole of his work in order to form a definite opinion. So he said that, okay, then why not consider this as a research paper and send it to some journal? Then some bigger version of the experts will look into it, and they will able to judge your work. Galois did not ignore Poisson's advice and began collecting all the mathematical manuscripts while he was still in prison. So he was there for many years in jail and continued publishing his idea until he released in the year 1832. He submitted his work on equation theory several times, but it was never published in his lifetime due to various events. The first attempt was refused by Cauchy. So Cauchy, when he sent his writing to Cauchy, Cauchy actually didn't understand his work. But in February 1930, following Cauchy's suggestion, he submitted it for the Academy's secretary, Joseph Fourier. So you all heard about Fourier series. So he then submitted to Fourier to be considered for picks of the Academy. Some award things he has submitted this. Unfortunately, Fourier died soon after, and his writing was lost. So he submitted to Cauchy. Cauchy didn't understand it, and he referred to Fourier to submit it. But unfortunately, when he submitted that, after a few years, Fourier died, and at the end, his writing was lost. So unfortunate. But remember, at that time, whatever Galois developed, it was not a problem for this mathematician, but whatever he developed, it took around 100 years to understand what Galois did. So Galois did it around at the age of 19 and 20. What he did was around 100 years advance of at that time. So no mathematician of that time could understand what Galois did. But after 100 years, then when the mathematics become more and more advanced, then people saw it and then they started understanding it, and then they started appreciating this. Before that, it was not an appreciation, because everybody thought that it's just a junk, something he has written what has no meaning and whatsoever. So in group theory, what is the important thing is that, so first of all, in the theory of equation, like the quantic equation, that means all the equations are being greater than equal to 5, that cannot be solved. Like Abel, Galois also did the same thing. But in case of group theory, he did a lot of things. He developed the concept what we known as normal subgroup. Also, he introduced the concept of finite field, also known as Galois field, in his honor. He constructed the general linear group over a prime field and calculated the order. He constructed the projective special linear group. Galois constructed them as fractional linear transformation. So you can understand that so much thing that he did it, and within his lifetime he couldn't get any kind of recognition. So just now I have mentioned that the Galois' most significant contribution to mathematics by far of his development of Galois theory. He realized that algebraic solution to a polynomial equation is related to the structure of a group of permutation associated with the roots of polynomials, the Galois group of that polynomial. So when you will be in master's degree, then you will study this Galois group, and then you will understand the idea how the polynomials and the permutations are related. So that was done by Galois. And it was the final day. It says that early in the morning, May 30, 1832, he was shot in a abdomen and died the following day. He was 20 years old. His last words to his brother Alfred were, "Don't cry, Alfred. I need all my courage to die at 20." So that was the last thing, and this is the memory of Galois. These things were there in Paris. So if one day you find any opportunity to visit Paris, you must go there. So that's all about all my talk. So any question or comments, if you have, please let me know.